Hi, my name is Ben Joseph Villamore,
And I'm Lucas Hugh.
and this is our research AI applications in vehicle trajectory data smoothing. Vehicular trajectory data, as captured by current camera sensor technology, has inaccuracies in the form of noise. When vehicle positional data is translated to velocity, acceleration, and jerk, the higher order derivative translations accentuate these inaccuracies. This noisy data represents the true vehicle position poorly and thus makes certain aspects of simulations and future trajectory positions unreliable. There exist many data smoothing algorithms, each with their own strengths and weaknesses. In our research, we tested various machine learning models and compared them to traditional mathematical models in an attempt to produce a model that could outperform these existing methods.
Our models are trained on the next generation simulation, also known as NGSIM vehicle trajectory dataset. We combine the velocity of a vehicle over time and the original dataset into a single array, then matched it with its corresponding data array in a manually smoothed, re-extracted dataset, which we use as ground truth data for training purposes. In total, we had over 1,200 raw to re-extracted pairs of arrays as training data, which we further split into training, testing, and validation data.
In pursuit to develop a model more capable than existing methods, we initially sought to utilize deep learning neural network models. Specifically, we trained models with a denoising autoencoder architecture. However, we discovered that our sample size of 1,200 training pairs was not sufficient for a complex deep learning model. We explored the capability for smoothing with simpler architectures, namely the random forest model and gradient boosting model, the XGBoost.
The machine learning models we trained are able to capture and smooth many flaws of the raw data, such as noise in the form of unnaturally sharp changes in velocity. The models performed exceptionally when the true data was relatively smooth, with varying deviation to the ground truth values. However, they struggled to capture the vehicle's change in velocity, most notably in deceleration. It may be possible to further improve the model's performance by tuning hyperparameters, but we believe that the limited quantity of training data constrains the machine learning methods from achieving greater accuracy and smoothing. Comparing exponential smoothing, moving average, and the machine learning models, we see that the traditional methods stuck closely to the raw velocity curve and thus often still deviated significantly from the re-extracted values. The machine learning models were able to better predict the correct values in certain scenarios, specifically when noise created significant deviations from the true values. Overall, the machine learning models had inconsistent results with significantly better performance at its peak, but poor performance at its worst.